Okay, so now I'm going to briefly discuss what are some of the benefits of taking this optimization perspective in dealing with problems, say, like the eigenvalue problem. These are the benefits of the optimization approach. And a big part of it is that the optimization framework is really quite general. It's like, and there's a huge body of theoretical analysis which comes with it, right? So one of this has to do with the question of convergence. So the optimization framework provides sort of very general set of convergence results. In particular, sort of near global convergence. And oftentimes they are fairly agnostic to the specifics of the problem. Sort of reasonably. Okay, and the other thing has to do with the rate of convergence, right? So the analysis optimization algorithms oftentimes also give you things about the rate of convergence. There is also sort of results, where there are also results on the rate of convergence. Sort of both linear rates of convergence as well as superlinear rates of convergence. Okay, and then the other thing is that, so the third thing is that for large-scale problems, by which we mean, say, things involving large matrices, right, often do not want to use sort of direct matrix factorization methods. It is preferable to make use of A only in the form of the operator. Which is to say that you don't directly work with A, it's like, but you think of it as operators X in a vector. So you look at X maps to A of X, and such methods are called matrix-free methods. Okay. So usually what happens is that for large-scale problems, you have very large matrices, but they tend to be very sparse. Okay, so that means only a small number of entries, a small fraction of the entries are non-zero, or at least it's like have entries which are large in some appropriate sense of the word. Okay, and when you do that, it's like you tend not to represent, or you tend not to store the matrix as a array of say n by n entries. Instead, it's like you store the entries in a sparser way, say like a linked list, where you only sort of store, say, the non-zero entries. So in those situations, it's like having that matrix act on a vector, for example, is quite fast because, as I said, it's like the matrix is sparse. It's large, but it's sparse, and so it only has a relatively small number of non-zero entries. And so doing something like a matrix vector product is cheap because it has to do, you take advantage of that sparse structure. Okay, so in any case, these are sort of some reasons it's like why it is sometimes preferable to look at this problem. It's like of it's like matrix problems like the eigenvalue problem, generalized eigenvalue problem, as an optimization framework, primarily because there's a huge body of theoretical tools which come into play. It's like by looking at it from the point of view optimization, both in terms of near global convergence as well as the rates of convergence, and it's like the way it's like the algorithms are developed. It's in this setting. They're essentially iterative methods. It's like, and oftentimes it's like they can be cast in this kind of matrix-free framework, which allows you to take advantage of the sparsity structure of a large-scale problem. Okay, so let me just stop here for now.